So last time I was trying to convince you that quasicrystals are interesting and that it makes sense to consider mathematical quasicrystals and spectral problems related to quasicrystals. And even in one-dimensional case, it's a non-trivial and interesting problem. So we suggested several models for one-dimensional quasicrystals. Let me shortly remind what models we considered last time. The most prominent model for one-dimensional quasicrystal is a Fibonacci Hamiltonian. So we want to consider a sequence of numbers, zeros and lambdas. Lambda is a coupling constant, and that sequence is given explicitly by the following rotation model. So you have a rotation of a circle by golden mean, you have an interval in a circle, and you just follow the orbit of zero. If the nth iterate belongs to that interval, then you put lambda. If it doesn't belong to the interval, you put zero. So you get a sequence of zeros and lambdas. And then you consider discrete Schrödinger operator where potential is given by that sequence. So the question, it's a self-adjoint operator, so bounded. So the spectrum must be a compact set of the real lines. So the question is, what is the spectrum and what can you say about the properties of that spectrum? The reason why we want to consider exactly this rotation number is because the sequence that you get in this case, not only a Sturmian sequence, the one that is given by rotations, but also a substitution sequence. And we discussed last time that if you consider Fibonacci substitution, this substitution, then it generates some sequence just by subsequent application of that substitution. And you can take the limit and you will get an infinite sequence of zeros and ones. And due to the numerical properties of the golden mean, that will be exactly the same sequence that you would obtain from that rotation model. We also considered a couple of other substitutions, Su-Morse sequence that is given by that substitution, and period doubling substitution that is given here. And actually, there is no special properties that distinguish them too much from other substitutions. So physicists consider them frequently just because it's the simplest substitutions that you can find. But actually, of course, you want to get everything that you can about general substitutions, maybe with some restrictions, and later we will discuss some of those results. Another model for one-dimensional quasicrystals that we discussed last time was the model given by the same discrete Schrödinger operator, but with different class of potentials. Those are Sturmian sequences. And we discussed that you can define complexity of a sequence, for example, in the following way. You consider the number of different words of the given length n, and then you just try to understand how fast that number of words grows. If you have a sequence which is periodic or eventually periodic, then this number is necessarily bounded. And it's known that this number for a sequence which is not eventually periodic should be at least n plus 1 for each n. And therefore, it makes sense to consider the class of sequences where exactly this bound is achieved. The simplest sequences that are more complex than periodic or eventually periodic sequences. And we also mentioned that what you get in this case can be easily described as rotation sequences of this form. So once again, you take some irrational alpha. Now there is no restriction on alpha, and you take take some orbit, some initial point. Now not necessarily zero, and then you just do exactly the same as we did it for a Fibonacci sequence. So for Fibonacci sequence, explicitly you get this alpha and this initial condition, and on the boundaries of the interval, you should take exactly the first version. And it's known that Sturmian sequences are exactly the sequences that can be obtained using this procedure. So what can we say about the spectrum in those models? What is known? First of all, it's known that if you take the Fibonacci Hamiltonian, then the spectrum is a contraset of zero measure. That was proven by Andreas Schutte in 1989 as a result of a sequence of several papers. Later, period doubling potential was killed, and Belisard and Kossars proved that in this case you also get a contraset of zero measure for any non-zero coupling constant. Later, Morse potential was killed, and the result is exactly the same. The spectrum for any non-zero coupling constant is a counterset of zero measure. If you have a counterset of zero measure, it doesn't apply it immediately, but it's an evidence that the operator must be singular continuous. Because it's known that if the spectrum has positive Lebesgue measure, then it must be absolutely continuous component. And if you have a counterset of zero measure, then it means that a C component doesn't exist. So that gives you some information that you should not expect nice transport properties. You should expect something different. So I'm not talking about spectral properties in terms of a C, PU point, and singular continuous spectra here, but I can shortly mention what is known. It's known for all those sequences that a C spectrum doesn't exist since you have zero measure. It's known that for many of them, it's known that pure point spectrum doesn't exist, except Morse potential. Amazingly enough, this one is still standing open problem. It's not known whether, if you consider a discrete Schrodinger operator with Morse potentials, that you don't have any eigenvalues. Everybody believes that it's the case. Nobody can prove that. And it's curious that the main feature of Morse sequence is exactly something that doesn't allow you to prove it. The most popular way to prove absence of eigenvalues in this case is so-called Garden argument. And Garden argument is the following. Suppose that you have in a sequence finite words that you can encounter 3 times in a row. And you can do that for finite words of arbitrary large length. Then this is enough to prove that there are no eigenvalues. But Morse sequence is exactly the sequence where you don't have any word that appears 3 times in a row. And the Gordon argument doesn't work. So this is an open problem. So that's roughly speaking what it implies. All right. So for those substitution sequences that we considered, we kind of settled the question on the topological level. For Sturmian sequences, it's also known. Belisard and co-authors proved that spectrum for any initial condition, for any rational rotation number, the spectrum is necessarily a counterset of zero measure. And therefore, in all the cases that we considered, we have essentially the same result. So the first idea is, well, maybe there is some general common feature of all those sequences that forces the spectrum to be a counterset of zero measure. And it turns out that this is indeed the case, but in order to see that, we need to incorporate all our models, all our operators, into the framework of the general theory of ergodic discrete Schrodinger operators. So this is actually the whole setting of that general theory. The setting is the following. You have some phase space, whatever it is. You have some homeomorphism of that phase space, some map. You have some invariant measure of that homeomorphism. And you have some function, which is not too bad, real valued function on that phase space. Now what you can do, you can pick a point in the phase space, start to iterate the point, and read off the function. That will give you the sequence of numbers. Just take that sequence of numbers as a potential of the discrete Schrodinger operator, and you will get some class of operators, because depending on the initial condition, you will get different sequences. And in many cases, you have to fix the measure because measure is not unique, but in all the cases that we are going to consider, that measure is going to be unique, so it's not a question what measure to take. And let's compare what we have in our case to that general setting. You have Fibonacci potential, which is given by this formula, which is just one very specific particular sequence. So it's not quite clear immediately what should be taken as that homeomorphism, as that phase space, and so on and so forth. But actually, it's really easy to incorporate that sequence into the general framework. Here's what you can do. Let's consider Okay, we're considering the space of sequences. So let's forget now about coupling constants. So we just consider a space of sequences of zeros and ones. And the space of all sequences of zeros and ones is just sigma 2. Just it smells horseshoe in a sense. And then let's consider all the sequences such that the set of finite words that you can find there is exactly the same as the set of finite words that you can find in a Fibonacci sequence. That will give you some compact subset in sigma 2. And the function that you want to consider is the simplest possible function. So if you think about horseshoe, it's just 0 on one leg of the horseshoe and 1 on another leg of the horseshoe. Or in terms of sequences, it's just the function that depends only on 0 element of the sequence, 1 if the element is 1, or 0 if the element is 0. And the transformation is just a Bernoulli, topological Bernoulli shift. So that gives you exactly what you want. And if you're not very comfortable with that finite word thing, I can suggest a constructive procedure to get that set. So Fibonacci substitution sequence is just one-sided sequence. So what I want to do, I want to complete that sequence any way you want, to the left, and then you get a point in sigma 2. Take topological Bernoulli shift and orbit of that point under topological Bernoulli shift, and take omega limit set. Notice that whatever you put on the left doesn't influence anyhow the result, because all those elements are killed, you forget them. And you get some nice set, which is a compact subset of counter set, so it's counter set itself. And you have, it must be invariant, because it's an omega limit set. And that's exactly what you get. It's not hard to see that those two constructions give you exactly the same set. So it turns out that if, it's a general statement, not necessarily for our case, if your transformation is strictly ergodic, that is minimal, and has unique invariant probability Borel measure, then the spectrum of the corresponding Schrödinger operator doesn't actually depend on the initial point. And therefore, in the future, I will just omit that dependence of the spectrum on the initial point. We have just a spectrum of that family, so it's the same spectrum for any element. By the way, I forgot to mention that let's for example consider the Fibonacci sequence. So what is going to be that that set and that homeomorphism on that set if you implement that construction for that particular Fibonacci sequence? We know that initially we had that here. We know that this is a rotation sequence. And so what happens actually, you get the set of all possible initial conditions on a circle. So there is a temptation to say that this set is a circle, but certainly it's not, it's a counter set. And the reason why it's counter set is exactly because you have two different possibilities here. You can include one point or another point of that interval. So what happens, it is a circle, but in that circle you take an orbit of 0, and each point of that orbit of 0 is split into 2 points. So roughly speaking, you have something very similar to the Denjoy counterexample. You have an orbit of a rotation of a circle, and you incorporate some small interval, and whatever is left is a counter set, and you have a rotation on that counter set. And that's a system that you can find in the full topological Bernoulli shift, and that's exactly the system that you will get if you apply this construction to the Fibonacci substitution sequence. And now we are ready to formulate the general statement. First of all, let me introduce the class of systems. So we will consider subshift of the full Bernoulli shift, strictly ergodic, and we will assume that it satisfies so-called Bashirnitsin condition. The condition is the following. Take any finite word that you can find inside of that sequence. Let's take the measure of the cylinder which is related to this finite word. And let's look what happens to this product. Let's take the minimum over all the words of given length. And what we want a lim sup to be positive. Now, that looks a little bit weird, but let's try to understand what's going on here. For example, let's consider first random sequence. In the random sequence for a given n, you expect to have 2 to the power n different finite words of the length n. And therefore, just by the pigeonhole principle, for some of those words, this measure should be exponentially small. And therefore, this minimum should be small. And therefore, what you get here is 0. And therefore, Bashir-Nielsen condition cannot be satisfied. On the other hand, for periodic sequences, it's definitely satisfied. And so what is required here that the length of words of, roughly speaking, the number of words of the length n grows not faster than linearly. And roughly speaking, each of those words appears with more or less the same frequency. Notice that this measure is exactly the frequency of appearance of a given word. And if you have that situation, then we say that Bashir-Nielsen condition holds. David Damanik and Daniel Lenz proved that as soon as you have Bashir-Nielsen condition for the system, then the spectrum is a counter set of zero measure. And all the examples that we considered before, all the substitution sequences that we considered and Sturman sequences that we considered, they do satisfy the Bashir-Nielsen condition, even if sometimes it's not too easy to check. So this is kind of strongest hammer that existed at that moment. Later, Liu, a Chinese mathematician, gave explicit example of a sequence where he was able to prove that the spectrum of the corresponding discrete Schrödinger operator is a counter set of zero measure, but which does not satisfy the Bashir-Nielsen condition. So this condition is sufficient but not necessary. So let me give one more example where Bashir-Nielsen condition immediately gives you the answer. Let's consider substitutions that are primitive. We will call that substitution as primitive if the image of each element, at least if you apply substitution several times, is going to contain all other elements from the alphabet. Here the definition is given for the alphabet that contains only 2 symbols. Roughly speaking, all interesting substitutions are non-primitive, primitive, because if you have a non-primitive thing, then roughly speaking, it means that you have some factor which is primitive. For example, one of the simplest cases, let's send 0 to 1 and 1 to 0. Then you will get 0, 1, 0, 1, 0. So that's not something interesting. So whatever interesting case you have, it will be primitive. For example, all the substitutions that we considered certainly primitive. And for primitive substitutions, the measure that you get there is exactly the frequency of appearance of the words, and it's possible to prove that Bashir-Nielsen condition is satisfied, and therefore for all primitive substitutions, the corresponding discrete Schrödinger operator has a spectrum which is a counter set of zero measure. All right, so in all possible cases that we had, the spectrum is a counter set of zero measure. Next question. What else can you say? You have some counter set of zero measure. Is it dynamically defined counter set? Can you say something about Hausdorff dimension, box counting dimension, some other quantitative characteristics of those sets? Can you establish the asymptotics of those characteristics for complex constants that are large and small, and so on and so forth? So what would be the next step, and how to understand what happens there? Notice that it's certainly mathematically interesting, but it's also physically relevant because, for example, the Hausdorff dimension of the spectrum is responsible for the speed of transport of the wave packets and so on. That's exactly what I'm going to talk about. So, first of all, I want to explain how the ergodic family of Schrödinger operators give rise to a cocycle of some special form, so-called Schrödinger cocycle. So let's see. we want to study the properties of this operator. Now, what is the spectrum? The spectrum is a set of eigenvalues. Well, that's certainly not true. It's true only in five-dimensional case. But let's pretend that we don't know about it. So we are trying to find eigenvalues. So we're trying to solve this equation. HU is equal to U multiplied by some eigenvalue E. E is a real number. So we are looking for energies such that this equation is solvable. Well, notice that if you have a solution of this equation, then if you have two subsequent elements of a sequence U that satisfies this equation, then you immediately know the next element of the sequence U just from that equation, just from here, right? And therefore, if you pick any vector, say U0 and U1, then it defines completely all the other elements of U, and in order to define it, you need to multiply those matrices over the orbit of the initial point under that homeomorphism that defines the family of the Schrödinger potentials. So let's introduce this matrix. Let's denote this matrix in this way. Those matrices are called transfer matrices. And what you want to do, you want to take some initial condition, U0, U1, so initial condition is two-dimensional. And then you want to multiply all those matrices, and that will give you the value un plus 1 of that solution of the Schrödinger equation. What you have is certainly a cocycle over that homeomorphism that defines the potentials. So for each point, you have a transfer matrix that is kind of attached to that point. You just travel over the phase space under your homeomorphism, and you take the product of those matrices. That's classical cocycle. That is called Schrödinger cocycle in this case. And let's define the set of energies such that the Schrödinger cocycle is uniformly hyperbolic. This is exactly the definition of uniformly hyperbolic cocycle, right? So for each energy, we can ask whether the cocycle is going to be uniformly hyperbolic or not. And it turns out that it's exactly what determines whether a given energy is in the spectrum or not. Namely, let's restrict ourselves to strictly ergodic potentials, just not to care about what measure to choose and so on. There is only one measure. Then for any initial condition, the spectrum of the operator, we already know that it actually doesn't depend on the initial condition, is exactly the set of energies for which this cocycle is not uniformly hyperbolic. Okay? So this is one geometrical description, the dynamical description of the spectrum, and it's extremely useful and was used during last decade by lots of groups of people for different physical models. Let me give just one example. The recent one, Avila, Bocchi, and Damanik proved much more. I just take one of the results from that paper. They proved that if you take some strictly ergodic transformation, let's restrict ourselves to subshifts, then for generic C0 potential, the spectrum of the corresponding operator is necessarily counterset. So how can you do that? You consider instead the set of Schrödinger cocycles, and what you are trying to do, you are trying to make a perturbation of the potential of that function f in such a way that cocycle becomes uniformly hyperbolic on the open and dense set of energies. And it's possible to do that, and that implies this result. Notice that here they do not claim that this counterset is of zero measure, and this is not actually true. For example, there are lots of examples, physically relevant examples, where the spectrum of the corresponding operator is a counterset of positive measure. For example, Olmos-Monsieur operator. Recently, Artur Avila and Lana Zhytomyrska proved lots of results regarding that operator, and in particular, they proved that the spectrum is a counterset of zero measure, of non-zero measure for all values of the coupling constant except one critical value. This is so-called 10 Martini problem. Okay. But in our case, it's more convenient to go in a different direction. So instead of considering Schrödinger cocycle, we will consider a little bit different thing. So remember that we consider Schrödinger substitution potential, and that's given by substitution, and the lengths of those finite words that we generate in that substitution are exactly the Fibonacci numbers. So let's take those products of those transfer matrices over the length of Fibonacci numbers. Then just the fact that the potential was given by substitution implies that you have a recurrence relation for that sequence of matrices, namely this relation. That's exactly how the sequences of zeros and ones were generated, and hence the sequence of matrices will be generated exactly in the same way. And notice, I didn't mention it right away, that each of those transfer matrices is a SL2R matrix. The determinant is equal to -1. The determinant is equal to 1. And therefore, if you are interested in the properties of that matrix, the next most important number is certainly the trace of that matrix. So let's consider the traces, or it's traditional to consider half traces in this case actually. Let's consider half traces of those matrices. It turns out that those half traces, that's a sequence of real numbers, and that sequence of real numbers satisfies the following recurrent property. And that's really easy to see. So let's see. Okay, xk plus 1 is half trace of this matrix. We substitute the product due to that substitution recurrence rule for the matrices there. We substitute it twice. We use the fact that the trace of AB is equal to the trace of BA. You get the square of the matrix here. Then you use the Kelly-Hamilton theorem here. And then you just take traces once again. And that's all. So you must have that relation, and notice that all you used here is that this is a sequence of SL2R matrices, nothing else. You did not use the specific form of the matrices. And this is an important remark, because in other physical models where you are trying to study, instead of electronic properties, for example, you are trying to study magnetic properties of quasicrystals or photonic properties of quasicrystals. And recently, physicists started to study phononic quasicrystals. So they're trying to understand how the sound can be transferred in quasicrystals. It turns out that it doesn't transfer there quite well, and that's very good, because you can use some artificial materials that are noise isolating and very thin at the same time, for example. So there are some really strange applications, but you can study all of them just using this relation, because you didn't use the specific form of the matrices. All right. So in our case, for the first several matrices, and it's more convenient, instead of x0, x1, and x2, consider x minus 1, x0, and x1. It turns out that the half traces have this form. So energy is energy, and lambda is a coupling constant. And now you reduce the problem to the following: you get a given energy. You consider that set of 3 numbers, which is an initial condition, and you start iterating this trace map. You just want to know what happens with that sequence of numbers, and due to so we don't want that cocycle to be hyperbolic. If it's hyperbolic, then the trace should grow. We don't want the trace to grow, and if it doesn't grow, then probably we're in a spectrum. And this is exactly what happens. The point that corresponds to the given energy, so given energy belongs to the spectrum if and only if the corresponding point, this point, under the iteration of this trace map has bounded semi-orbit. So you apply this map and you always get something bounded. And now you can forget completely about the spectral theory. Now you have the following simple dynamical problem. You have a line parameterized by some parameter E. Any questions? No. You have a line parameterized by some parameter E. You have in 3-dimensional space. You have a polynomial map, this specific map in 3-dimensional space, and you want to know which exactly points of that line go to infinity and which point have bounded semi-orbits. And, well, that's all. So let's try to study the properties of this map more accurately. First of all, what is interesting is that this map has a first integral. So this cubic polynomial is preserved under the action of the trace map, and therefore it makes sense to consider the level surfaces of that function. That function is usually called Freaky-Vogt invariant, and restrict our map into that level surface. The level surface that corresponds to zero value of the coupling constant is a special one. It's called Kelly cubic. It's also not hard to show that the line of initial condition that corresponds to a given coupling constant will be entirely on the level surface that corresponds to that coupling constant. And here is how the Kelly cubic looks like. So you have a central part which is invariant. You have 4 conic singularities, and you have 4 non-compact cones that goes to infinity. The map restricted to the central part is going to be Pseudo-Nosov transformation. The line of initial conditions is going to be the line that contains this singularity and that singularity. So if you take that line and look at the set of points that remain bounded, you will get exactly the interval between those 2 points. And that exactly corresponds to the fact that if you take the spectrum of free Laplacian, you get an interval from -2 to 2. And then what you want to do, you want to take non-zero coupling constant. Then singularities disappear. You have some small necks, but nevertheless you have a connected surface, non-compact surface. The line will still be very close to the line that connected to those 2 singularities, but it will be entirely on that surface. And then the picture just can be continuously extended. So what are the properties of this? Yes. Can you say louder? There is an algebraic interpretation of that first integral. So, okay, let me return to. Okay. So first of all, I have to say that the trace map is a very interesting object, and spectral theory is by far not the only place where this trace map appears. It appears in analysis. It's related to properties of Pinlev-Six equation. It appears in number theory. It's related to Markov triples. It appears in the theory of Fuchsian groups. It appears in geometry. It appears everywhere. The reason why it appears everywhere is the following. It's purely algebraic reason. Let's consider the representation of a free group with 2 generators in SL2C. This representation is totally defined if you know the image of the first generator and the image of the second generator. Now let's factorize over the conjugacies over the group of automorphisms in SL2C. Then it turns out that the set of invariants is just 3 complex numbers: the trace of the first image, the trace of the second image, and the trace of the product. And that gives you 3-dimensional space. And then if you change the generators, that induces a polynomial change in that space of invariants. So for example, Fibonacci substitution can be interpreted as a change of those generators in a free group, and that induces exactly this trace map. Now, if you take the trace of the commutator, then what you get is exactly Freaky-Vogt invariant. Okay? So actual Freaky-Vogt invariant appeared in mathematical literature in 19th century, exactly due to this algebraic construction. And both Freaky and Vogt are quite ancient mathematicians, I would say. Okay. All right, so Martin Kazdaghly in his PhD thesis proved that if the value of the Freaky-Vogt invariant is large enough, so you are far away from the Kelly cubic, then the trace map is actually hyperbolic, which means that the set of all orbits that are bounded is going to be a hyperbolic horseshoe, and all other points will go to infinity either under positive or negative iterates. The way he proved it was more or less straightforward. So he just found the domain such that the first return map can be studied explicitly, and he explicitly gave the cone field and checked explicitly the cone condition for the cone field, and that implied that implied hyperbolicity, but on the other hand, that restricted him for large values because that projection that he wanted was available only for large values of the Fricke-Vogt invariant. Next, with David Damanic, we proved that the same result holds for small values of coupling constant, and the reason is because you can actually inherit hyperbolicity from the Cayley-cubic. On a Cayley-cubic, as I mentioned, and I will show that later more explicitly, you have pseudo-Anosov transformation, and when you increase coupling constant a little bit, increase lambda a little bit, then it turns out that hyperbolicity does not disappear. It will be inherited, and you will still get a hyperbolic set there. But then Serge Cantat completely closed the question and proved that it's hyperbolic for all values of positive values of Fricke-Vogt invariant, and he used methods of holomorphic dynamics. He used the results by Smiley and other people, and he used the criteria that allowed to compare absence of hyperbolicity for the holomorphic map with maximal possible entropy, and he proved that if you didn't have hyperbolicity, then you wouldn't get maximal entropy, and the fact that topological entropy is maximal possible just follows from geometrical reasons from the action on the fundamental groups. That's a very nice proof. Okay, now what are the consequences of that? So remember that initially our problem was the following. You have the trace map, you have the line of initial conditions, and you want to know which points on that line do not go to infinity under positive iterates. So you have a horseshoe. Now we know that you have a horseshoe, and all other, yes? I'm not restricting myself to the positive values of lambda. Lambda can be any just non-zero, but I restrict myself to the positive values of Fricke-Vogt invariant. So I want to consider only those surfaces that I showed on the picture, because if Fricke-Vogt invariant is smaller than zero, then the level surface will separate. It will not be connected anymore. It will contain four parts that will go to infinity, doesn't matter what, and it will also contain a sphere inside of Cayley-cubic. And that's a completely different story, and that I will discuss on the very last lecture. It's related to conservative dynamics. All right. So we have this line, and we want to understand what is a set of points that do not escape to infinity. But we have a horseshoe. And we have a stable set. So what is a set of points that do not escape to infinity under positive iterates? That's exactly the set of stable manifolds of that horseshoe. And you have a line, and suppose that this line is transversal to those stable manifolds. Then this intersection is a counter set of zero measure, and that's exactly that counter set of zero measure, which is a spectrum of the corresponding Fibonacci Hamiltonian. So it's not only this counter set of zero measure, but it's a dynamically defined counter set. And let me remind the definition. The dynamically defined counter set is a counter set that can be obtained as a result of application of iterated function system to the interval. So you have finite set of contractions, you apply them to the interval, you take the union of images, you apply those contractions to that union again and again, you get a nested sequence of compact set. The intersection gives you the counter set, and any counter set that can be obtained using this procedure is a dynamically defined counter set. How much time do I still have, if I have any? Okay, thank you. Okay, so dynamically defined counter sets have some very nice properties that distinguish them a lot from from general counter sets. It's known that they have zero measure. It's known that they are exact dimensional, so all the possible definitions of fractal dimensions must coincide. In particular, Hausdorff dimension and box counting dimensions must coincide. It's known that Hausdorff dimension locally is the same as globally, so you can take any point, any neighborhood of that point, and the Hausdorff dimension of that set intersected with that neighborhood will be exactly the same as the global Hausdorff dimension. It's known that if you change those generators a little bit, continuously, then the contraset will be changed continuously in the Hausdorff metric. And it's also known that if you have a family of contrasets, which is exactly our case because we have that coupling constant, which is a natural parameter, then analytic dependence of those generators on the parameter implies analytic dependence of the fractal dimension of that contraset on those parameters. And you can immediately transfer all those properties to the spectrum of the Fibonacci Hamiltonian. And, well, I will not repeat, but that's exactly the same list of results. But formulated in terms of the spectral theory. Well, that has some nice consequences and non-trivial consequences. For example, if you consider the Hausdorff dimension of the spectrum and you want to know what happens with that Hausdorff dimension if coupling constant is sent to infinity, for example, then it's possible to prove that the Hausdorff dimension goes to 0. And not only it goes to 0, but it goes to 0 with exactly the speed. One of the ingredients in the strategy of the proof is to estimate, to use the periodic approximations to estimate the covers that you can get out of the periodic approximations, and then to estimate Hausdorff dimension and box counting dimension separately, and then to use the fact that they must coincide. And if you use the fact that they must coincide, that gives the exact asymptotics for the Hausdorff dimension. Next, natural question, what happens if coupling constant is sent to 0? So what happens if the line, surface that you consider approach as a Kelly cubic? And instead of estimating the Hausdorff dimension, I would like to estimate a different quantity, the thickness. First of all, it will imply the result for Hausdorff dimension, and secondly, we will need it anyway when we consider the square Fibonacci Hamiltonian. So this is the definition of the thickness. If you have a contraset, let's assume that this contraset is obtained by removing open intervals. And let's just remove the largest interval first, the second largest second, and so on and so forth. After each removal, you know exactly what is left from the right and from the left. Let's consider the ratio of the length of the interval which is left from the right to the interval that you removed, and the same for the left interval. And let's consider the infimum over all those ratios. You will get a thickness of a contraset. And for example, the standard contraset has thickness 1 because each time you remove the interval which is exactly of the same length that you have from the left and from the right. It's known that thickness is related to Hausdorff dimension of the contraset. Namely, if the thickness tends to infinity, then Hausdorff dimension tends to 1, and this is the explicit estimate. And it turns out that it's possible to find explicit asymptotics of the thickness of the spectrum of the Fibonacci Hamiltonian if coupling constant tends to 0. Namely, it tends to infinity, roughly speaking, as 1 over coupling constant, 1 over lambda. And from the previous relation, it follows that you get an asymptotics for the Hausdorff dimension. The Hausdorff dimension in this case must tend to 1. It's interesting that it's not too easy to construct a non-trivial example of a discrete Schrödinger operator such that Hausdorff dimension doesn't tend to 1. But it's also not easy to prove that in a particular case it tends to 1. Arthur Avila gave an explicit example of a Hamiltonian where Hausdorff dimension of the spectrum does not tend to 1, even if the spectrum is a contraset of 0 measure when coupling constant tends to 0. Yes? No, you have to estimate denseness instead of thickness, and you can certainly do that. I just didn't want to introduce another thing. Yeah, sure. Okay. And here is, roughly speaking, what's going on. Here is how you can study this system. So first of all, let's make sure that what I said is correct, that the restriction of the trace map to the Kelly cubic is indeed Pseudo-Nosov transformation. Well, it's especially easy because not only I can explicitly say what what linear map of the torus can be considered as having this factor, but also I can explicitly present the semi-conjugacy. And so this is just a question of explicit checking. You can check explicitly that yes, this linear map of the torus has a factor which is exactly this map, a trace map, and therefore the trace map is pseudo-Anosov. And moreover, you can explicitly use this Markov partition. That Markov partition actually appeared in the initial paper by Martin Kazdaghli. He was trying to prove something for small values of coupling constants. And this Markov partition is very helpful. It's not the most economical one for the linear transformation of the torus. We can find one with smaller number of rectangles. But it's nice because it's symmetric with respect to the map x goes to minus x. And that's This is the hyperbolic map of the torus. Well, the square of this guy is exactly the cat map. Okay? So it's hyperbolic. And this is the Markov partition for this map. And this is the semi-conjugacy between this map and the trace map on the Kelly cubic. Now, this Markov partition is nice because it's symmetric, and the parts of the Markov partition marked with the same number here will be sent, they will be glued together. It's 2-to-1 map almost everywhere, and those elements of Markov partition will be sent to elements of the Markov partition of that pseudo-Anosov transformation. And so, you are given explicitly the Markov partition of that transformation. Well, now we want to take the cone field for the linear map, and we want to send that cone field to the Kelly cubic, and then we want to say that, well, after small perturbations, that cone field will give you hyperbolicity. Well, that's not that easy because the semi-conjugacy is certainly degenerate in the neighborhoods of preimages of those singularities. But nevertheless, even if it's degenerate, if you consider the action on the angles, so not on the vectors but on the directions, then it's not degenerate. So it doesn't change the angles too much. If you had an angle which is bounded from 0, it will remain bounded from 0, and therefore you have a nice cone field on that Kelly cubic nevertheless. And then we just need to study separately the behavior away from singularities, because away from singularities that cone field inherited from the linear transformation will give you the invariant cone field, hyperbolic cone field everywhere. But in the neighborhood of singularities, we need to study it separately. So let's take a closer look to the singularities. First of all, let's take the singularity which is a fixed point. The three others form the periodic point of period 3, and due to the symmetries, it's enough to consider just one of them. That singularity is one point on the line of periodic orbits of period 2, and this line is normally hyperbolic curve for the trace map. And since it's a normally hyperbolic curve, the strong stable, strong unstable manifolds of each point are going to be manifolds that belong to the corresponding surfaces of the Fricke-Vogt invariant. And since we know that it's normally hyperbolic, and there is no contraction and no expansion on the curve of those periodic points, then those benching conditions necessarily satisfied, and normally hyperbolic theory gives you the following: strong stable and strong unstable foliage manifolds for that curve of periodic points are well defined, smooth, and they are nicely and smoothly C1 foliated by strong stable and strong unstable one-dimensional manifolds of those points. And then what happens, something happens in the neighborhoods of the points, and in each neighborhood, actually, that Markov partition will be kind of splitted into two parts, so the boundaries do not coincide anymore. But nevertheless, you will still get a Markov partition, a nice Markov partition for the trace map on the level surface of Fricke-Vogt invariant for small values of the coupling constant. And that allows actually not only to claim that you have hyperbolicity, but also that you have explicit description of the dynamics. It's a topological Markov chain with this matrix because you explicitly presented the Markov partition. Okay. Okay. Well, then I will skip. I will skip the explanations. I will just say a couple of more words about another question that you can answer. So what's on this picture? The x coordinate is a coordinate of energies. Y coordinate is a coordinate of coupling constants. So let's do the following. Let's just, for each value of coupling constant, draw the spectrum of the corresponding operator. This is a picture that you will get. If coupling constant is 0, then the spectrum is the interval from -2 to 2. Immediately, as soon as coupling constant is not 0, the spectrum becomes a contraset of zero measure. But that's how those contrasets glue together. And what you can do, you can take one of the gaps here, and you can see that the gap should shrink when coupling constant tends to 0. It's natural to ask how fast it's going to shrink when coupling constant tends to 0. And this question was answered by Bellissard for Sumor's potential and by Bellissard with quasars for period doubling potentials. The results were quite amazing. For Sumor's potentials, for example, all the gaps shrinks to 0 polynomially fast, so faster than linearly. And for Sumor's potential, you have two types of gaps. Some of them shrinks linearly and some of them shrink super exponentially. And it turns out that in our case, all gaps shrinks linearly necessarily. Certainly the speed that limit is going to depend on the gap, but nevertheless it's linear for each gap. And it's really easy to see why it happens. So let me return to this picture. So the line of initial conditions is exactly this line. Now, what is the gap? The gap is the set of energies between those two strong stable manifolds of one of the singularities. You know exactly how those periodic points diverge when you switch on the parameter, just because you have explicit formulas. They diverge in such a way that the distance between them grows linearly with lambda. But at the same time, we know that the strong stable manifold is foliated, and that is a C1 foliation. And so the rate of convergence here must be exactly the same as the rate of convergence there. And so if you converge to 0 linearly here, then you should converge to 0 linearly there, even if, depending on the point of the intersection, that limit will be different. So I should stop here, and next time I will discuss some open problems related to other substitutions and other trace maps, as well as to Sturmian potentials and dynamical systems that are kind of resembles the properties of random dynamical systems. And then we will discuss the density of states measures and the relations to measures of maximum entropy of the trace map, and a nice application of thermodynamic formalism also will be shown.